All right. Try to clear things up here a bit. So this is the second in our lectures for organic chemistry, and the focus here is on functional groups and recognizing them in drawings. So we have about 14 functional groups to look for. And what I'm going to do is I'm going to give you the name of the functional group and what you're going to look for to recognize that functional group. So the first one is the easiest. It's an alkane. You're looking for carbon-carbon single bonds and carbon-carbon or carbon-hydrogen single bonds. So this would be an alkane. For an alkene, you're looking for something that has a carbon-carbon double bond. So this is an example of an alkene. Alkynes have a carbon-carbon triple bond. So here you can see a triple bond. How many carbons are in this structure? Well, there's a carbon here that's singly bonded to a carbon here. So that's 2 carbons. That's triply bonded to a carbon here. So that's 3 carbons. And that one's singly bonded to a carbon here. So that's 4 carbons. So there's 4 carbons shown there. Now, here's an aromatic. You look for a ring. So a ring means that you have 6 carbons. Well, not necessarily 6. You have 6. In this case, you do have 6 though, where they're all bonded to one another to form a ring of carbons. And here it has what looks like double bonds in the middle of each of these. Now, these are not actually double bonds because you could draw this and it's the same thing. Now, what would we call these things where the double bonds are moved around a bit? And these would be called resonance structures. So how do you draw a resonance hybrid where you could have these double bonds either every other set of carbons here or every other set of carbons here? Sometimes people draw it like this. Okay, and then there's also cycloalkanes where you just have a ring of carbons. So 1, 2, 3 in that ring, 1, 2, 3, 4. So these are collectively called hydrocarbons. Hydrocarbon is not a functional group. These are functional groups. The next set of functional groups we're going to look at are ones where you have something other than just carbon and hydrogen. So there are 4 that we're going to look at. I'm going to add one more here. There's the alcohol, where you have a carbon bonded to an OH. So this is an alcohol. Carbon bonded to a nitrogen. So this is an amine. And a carbon bonded to an oxygen, then to another carbon. So this is an ether. There's also something called a haloalkane or an alkyl halide. Now, an alkyl halide or haloalkane is something like this, where X is equal to fluorine, chlorine, bromine, or iodine. So an example of an haloalkane would be this. And this particular one is called chloroform. I don't know if you know this, but chloroform is that stuff that you see in the spy movies where they pour it onto a cloth and then they put it over someone's mouth and nose and it makes them pass out. So that's chloroform. It's a liquid at room temperature and it can cause you to pass out. Now, it turns out that chloroform is a bit of a problem. It's a cancer-causing agent. So here, chloroform is quite dangerous, and spies are no longer allowed to use it because of the inherent dangers in chloroform. Okay. Yeah, I know, that's a joke. Now, we have 5 more functional groups here. Now, these functional groups are called carbonyls because they all share a common feature. This is called a carbonyl group, but that's kind of a misnomer. It shouldn't be called a group. It's a feature. So here you have a carbon double bonded to an oxygen. That's a carbonyl, and it lends a certain type of reactivity to all of these molecules, but there are some individual differences between them. So we do have these functional groups that all have this carbonyl group. I've also heard it called a moiety. I'm not sure if I pronounced that right or said that right. I don't even know what that word means, but it's not quite a group. Okay. So here you can see that we have the aldehyde, which has a carbonyl bonded to a hydrogen. You have a ketone, which has a carbonyl bonded to two carbons, one on either side of the carbonyl carbon. By the way, this is called a carbonyl oxygen because it's part of a carbonyl and it's an oxygen. And this is called a carbonyl. Yeah, you already guessed it, carbon, because it's part of a carbonyl and it's the carbon. So here you have carbons bonded to either side of the carbonyl carbon for a ketone. Notice ketone does not have the letter Y in it. If you've ever heard of something called ketoacidosis, which can happen to a person who may have a problem with metabolism, like maybe diabetes, and they expel these ketones, which make them seem like they're drunk. It's called ketoacidosis. They're expelling ketones. Okay, there's also something called a carboxylic acid, which has this thing in here, and we've seen this before. This is a common feature in very weak acids. So the carbonyl carbon is bonded to an OH. And here you have an amide where the carbonyl carbon is bonded to a nitrogen. And in the ester, the carbonyl carbon is bonded to an O, then another carbon. Now I want to pull back some features here of some other functional groups that we just saw. And we want to understand, why are these different? So do you see how the amine here has a carbon bonded to a nitrogen? And here the amide has a carbonyl carbon bonded to a nitrogen. Why are these not the same functional group? And the answer is, when you have that double bonded oxygen on that carbon, that will make these guys react differently. So the carbonyl makes it a different functional group than if there is no carbonyl. So we can see that too with carboxylic acids, the COH and the COH here, they look similar. Why are these two different functional groups? The carbonyl carbon. Furthermore, with the ester, it looks a lot like an ether. COC, COC. What makes this an ester instead of an ether? The carbonyl carbon. So that's important when we're trying to recognize functional groups. So here I have a molecule where we're going to practice recognizing functional groups. So we've got, I spelled this wrong, aspartame. It's a sweetener. And it has the following line drawing here. So here we can see the line drawing, and maybe what we should do is we should practice filling in all the features, but we want to identify the functional groups. Here's what I like to do when I'm identifying functional groups. First, collect the aromatics. Secondly, recognize the carbonyls. Thirdly, do the amines, alcohols, ethers, alkyl halides, alkenes, and alkynes. Okay. For these, we don't really recognize alkanes and cycloalkanes because they're just far too common. Okay, so this aspartame, I've written down here again. So let's start off with the aromatics. Can you see that that's an aromatic? There we go. Now, I don't see any other aromatics, so I'm going to look for the carbonyls. Do you see that there's a carbonyl right here, carbon double bonded to an oxygen? So I want to look at that carbonyl and see if there is something bonded to it that's not a carbon. And here we do. So what do we call that? We call that a carboxylic acid. Now I'm going to look for more carbonyls. Do you see that's a carbonyl? So I'm going to look to the left and the right. And here I see there's a nitrogen. So I want to collect that. And we're going to call that an amide. And here's yet another carbonyl. And you can see that I've got an OC bonded to that. So this makes that an ester. So I've got 3 carbonyls here. Now, I see that carbonyl here, and I look at that, and that's a carbon. This would be an amide if the carbonyl was right there at that juncture, but it's not. So here I have a carbon bonded to a nitrogen, but no carbonyl carbon. That makes this an amine. So these are the functional groups that you would find in this molecule. Now, you might be wondering, what is this here and what is this here? Those are just alkanes. You'll find those in all different sorts of molecules. Let's go ahead and fill in the rest of this though. Let's make the Lewis structure. So I'm going to start here with this hydrogen. There's the hydrogen. I'm going to put a bond between the hydrogen and the oxygen. And then I'm going to go down, and then I'm going to put a carbon there, and then a double bond to the oxygen. And while I'm going along, I'm going to go ahead and put in the lone pairs on the oxygen so that it has an octet. Now we go up to a carbon. We go down to a carbon. We go down to a nitrogen. And here, I want to make sure for that H2, I put the hydrogens in like this and the lone pairs. And then we go up to this carbon, double bond to an oxygen, lone pairs on the oxygen, down to a nitrogen, and see that hydrogen, it's bonded to the nitrogen, so I'm going to go down like that, and then up to a carbon and a lone pair on that nitrogen so that it has an octet. And here, this carbon is that one right there, so I'm going to go up to another carbon, and I have a ring of carbons like that. And then I want to put those double bonds in. They aren't really double bonds. There's a resonance there. And then this goes down to a carbon with a double bonded oxygen, put in the lone pairs, goes up to an oxygen, put in the lone pairs, and down to a carbon. So the only thing I need to do now is put in the correct number of hydrogens on the different carbons. So this carbon has 1, 2, 3, 4 bonds. It's done. This carbon has 2 bonds, so I'm going to put in hydrogens. This carbon has 1, 2, 3 bonds, so I'm going to add a hydrogen. This carbon has 4 bonds, so it's good. This carbon, I only see 3 bonds, so I'm going to put in a hydrogen. This carbon, I see 2 bonds, so I'm going to add 2 hydrogens. This carbon has 4 bonds. This one has 3 bonds, so I'm going to add a hydrogen. This one has 3 bonds, add a hydrogen. This one has 3 bonds, add a hydrogen. This one has 3 bonds, add a hydrogen. And this one has 3 bonds, add a hydrogen. This carbon has 4 bonds, so it's done. This carbon has 1 bond, so I'm going to add 3 hydrogens. So this is the Lewis structure for this molecule. We put in all the lone pairs, all the hydrogens, all of the atoms. And what is the molecular formula here? Well, that's a tough one, but we can do it. First, we're going to count carbons because we're going to do this in alphabetical order. Carbon, hydrogens, nitrogens, and then oxygens. And perhaps we go with the easiest ones first. I think nitrogens will be the easiest. And I think looking at this structure, it's easier to see the nitrogens than this one. 1, 2 nitrogens. How many oxygens? 1, 2, 3, 4, 5. Now, how many carbons? Well, let's count them. 1, 2, 3, 4, 5, 6, 7, 8, plus the 6. So what's 8 plus 6? 14? Okay, now hydrogens are clearly going to be the toughest ones to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And there's the molecular formula. Now, what would the structural formula look like? It looked just like this, but without the lone pairs. Okay, what I'm doing right now is I'm taking a last look to make sure that I have not forgotten any hydrogens on any of the carbons, because that would put this count off. Okay, so that's how you recognize functional groups in a molecule. That's how you turn this line drawing into a Lewis structure. I didn't show you how to make the structural formula, but you realize it's this without the lone pairs. And finally, this is how you get the molecular formula. So you want to be able to recognize functional groups in molecules Another important aspect of this is to recognize that molecules often have more than one functional group in them. However, here's what we're supposed to understand. This aromatic is going to react like an aromatic in any other molecule. This amine is going to react like an amine in any other molecule, and so forth and so on. All right. That's the end of our second lecture in the organic chemistry. The next lecture is going to be about hydrocarbons. Thank you for listening, and tune into the next lecture.